a bit more on the ramifications of an electric field. We've seen in a couple other videos our model of bulk matter here, which is a bunch of protons, the red dots, and a bunch of electrons, which are swimming around it here. And for this case here, we'll just say that this matter here, this is a conductor. So, of course, the electrons are very free to move around. And what we've done in the case of the conductor now is we've brought a positively charged rod near that conductor. So what we know now about the electric field, and we've seen in other videos, is that the electric field due to this rod will fill all of space around it with the electric field lines because of the rod, and the electric field lines will permeate through the conductor. So what will happen is these are positive, so we know these electric field lines will come out in all directions. We'll learn more about these types of distributions in a minute here in another video. But the electric field lines sort of go in all directions, but generally we know because it's a positively charged rod, the electric field lines will be in a direction away from the rod itself. So it's going to look something like this, including where the matter is. So now you look at, well, what happens in the matter now? Well, we have all these protons which cannot move, but these electrons that can move because it's a conductor, and they're now in an electric field. So what happens when matter gets in an electric field? Well, as we saw in a previous video, there'll be a force on it. In fact, the relation between force and electric field is that force is equal to Q times electric field, something like this. So if you have a charge, say like an electron, here, Q, in an electric field E, there will be a force on it. But remember, for an electron now, that Q is less than 0 because electrons are negatively charged. So it turns out here that what electrons do, so electrons always, they always move opposite to E field lines. So if you have some electric field lines, the electrons always move in an opposite direction because of their negative charge. So in this case here, the electric field is up because of the rod right here. The electrons always move against electric field lines, so all the electrons are going to move down. So in effect, what we'll see is all these electrons are immersed in electric field lines because of the conductor. Let me even draw a few more in here to really illustrate the point that the conductor is really immersed in all these upwards pointing electric field lines here because of this conductor right here. So what's going to happen is all the electrons are going to start moving down. So I won't try to erase all the purple ones. Just imagine that they all sort of move down to this region right here. They bump up against the edge of the very conductor they're in themselves, but the electric field has pulled them down. So that's how, with nothing intervening right here between, that's how we get the electrons actually to move down. It's that electric field, once again. The material, in this case the conductor, is immersed in the electric field because of the positively charged rod. And so we get this, the picture is consistent now that the conductors become polarized. If all the negative charges move down, then there's going to be a deficiency of negative charges in this top part over here. There's going to be a bunch of positive charge on this side of the conductor, so the conductors become polarized once again. So two ways of thinking about it: the electrons have moved down, and they actually do move down in the conductor. And the other way to think about it is if electrons move opposite to the electric field lines, positive charges must move parallel to electric field lines, and they do, because remember, for positive charges, Q is greater than 0. So if you have this force law here, that F is equal to QE, with Q being a positive number, positive charges move parallel to E field lines because there's no negative charge sending them in the opposite direction. So we sort of see that in the polarization of the conductor right here, that the negative charges have moved down opposite the electric field lines, and the positive charges, if those were the things that were mobile, have moved up, although we know that positive charges really mean a deficiency of negative charges in a system like this. So the last one to look at is, again, to keep that rod there, but instead of having a conductor in there, we'll put an insulator in there. What happens to the insulator? So here's your bulk material right here. Here's the protons making up the structure. Don't move. Fixed in there. And now we'll put a bunch of little electrons in there. And remember, in the insulator, we have to think of this little dipole model in here, where there's sort of these little electron pairs that are paired up with their host atoms in there. They can't move very much, but we have these little atoms, or these little dipoles in here that we think about. So there's a dipole right there, and there's a dipole right there. These are the things that are more or less fixed in the insulator. They can't move around, but they can rotate a bit. And so the question then, if I bring that positive rod again near an insulator now, so here's the rod, and let's say it's all positively charged. What happens, given that this is an insulator now? What's going to happen? Well, once again, we'll see the same thing happen. We'll see the insulator be completely immersed in the electric field lines because of this charged rod. Electric field lines go in all directions throughout space and positively charged, so they'll be pointing away from the rod. away, away, away like that, something like this, all pointing away like that. So what we have now is we have these little dipoles or atoms which can't move, but they are still immersed in electric field. So what happens? Let's just go to a little aside here and see if we can just sort of work that out maybe down here. What happens when you immerse a dipole in an electric field? Like something like this. So here's a little dipole right here, a positive and negative, maybe it's like this. And suppose that it's immersed in an electric field that looks like this, and maybe the electric field is pointing in this direction here. Okay, it's pointing to the right. So what will happen is, of course, we know that the positive charge moves parallel to the field, and the negative charge would like to move, I'll just sort of draw this as anti-parallel to the field. Let me draw these little arrows. The positive charge parallel to the field, the negative charge anti-parallel to the field. So what will happen is the positive charge here in this dipole would really like to move this way, parallel to the field, and the negative charge would really like to move that way, anti-parallel to the field. That's a rotation. If you have something in the top half wants to move to the right and the lower part wants to move to the left, it'll rotate. So all told, what will happen is this dipole here is going to start to rotate until it actually looks like this. It's going to look something like that. So that's the most it can move. This is the positive charge aligned with the field, the negative charge trying to go that way. This thing will actually go like this and rotate until it looks like that. So these dipoles here, you could think of, they align with the field. Of course, you can think of the alignment as definitely being that positive charge and that negative charge doing what they're doing, but the positive charge moves with the field, the negative charge wants to move anti the field, and that causes the rotation, as we might guess. And so if we go back to the bulk material here, the conductor here, then what we can think of is when you immerse an electric field like this, the dipoles will then align themselves with the electric field. So I'll get a different color and just sort of draw the dipoles in very big so we can see what we're talking about here. But if we have a bunch of dipoles aligned with the field, here's a big dipole right here. We'll see the positive here, negative down here, positive here, negative. All the dipoles are sort of going to align like this. Again, the positives are up, the negatives are down because the positive want to align with the field, the negatives want to align against the field. Keep drawing here in a better color. Like this, same thing's going to happen up here. All the dipoles, they don't move, but they align and rotate. And we saw a different video where we saw that in the interior region of this matter right here, we sort of get a net neutral in here, but we do get that surface charge happening once again, where all these positive charges up here are on the surface of the insulator like that, and all these negative charges down here are on the bottom surface like that. So what we get is the insulator becomes polarized. So if I sort of draw the bulk material like this over here, when it's in the electric field, all the negative charges will gather down there, all the positive charges will gather up here, and in the interior there's sort of a net neutral in there. So it's not like anything moved in there, but that's just the way all the dipoles or the atoms have aligned because you've immersed the conductor in an electric field.